Hi, so this is the second video in a two-part series where we're talking about rethinking derivatives. Okay, so I talked about last time about how we can think of functions as actions. So we have the number line, and we think of a function f as doing something to the number line. Right? So maybe this point constant here, this point constant here, something like that. So last time I talked about functions from to and now we're going to talk about functions more generally to n to m. So just for the sake of simplicity, we're going to let n equals m equals 2, and let's go ahead and look at an example function. So let's look at f is going to go from R2 to R2, and the function we're going to look at is f x1 x2 is equal to x1 squared plus x2 and 3x1 minus x2 squared. So we can kind of think of this as like a function f1 and this as a function f2. Okay, so what does this function look like? So if we go back to thinking of functions as actions, so if we wanted to graph this, really it would be in four-dimensional space. Right? We can't really visualize that. So but if we think of functions as actions, and we have some f here, we can just kind of think of two coordinate axes. And if we want to, let's zoom in at this point right here. Let's say it's 1, 1. And maybe that gets mapped to some other point here, f of 1, 1. Okay, so before we had some dx or some neighborhood that kind of got mapped, and the derivative was essentially how much that neighborhood got stretched. So now what I'm going to do is I'm going to take a tiny vector, which is like my neighborhood dx, and a tiny vector dy. So instead of having a tiny interval, now I have this tiny area that's adjacent to this point 1, 1. And that's going to get mapped somewhere over here. Essentially, so how do we take a derivative of this? What's the derivative of this function? So you may have learned of the Jacobian matrix. So the Jacobian is we're going to take the partial of f1 with respect to x1, partial of f1 with x2, partial f2 with respect to x1, and with respect to x2. And we can see pretty easily, if we just do some routine computations, this is going to be the Jacobian. Right? And I can take, so this is the Jacobian, this right here, for all intents and purposes, is the Jacobian matrix. And I can take the determinant of this, if I wanted to, and that would to be minus 4x1 minus 3, and that would be the determinant. But let's think about what this is saying. So we can think of matrices as linear transformations. So this is a linear transformation, and I can think of this dx as a basis, this dx and dy as basis vectors. So dx, I'm going to go ahead and relabel this. So this is x1 and this is x2. And this should be y1. And yeah, I'll call this y1 and I'll call this y2. That's going to be much easier. Right. So this should be dx1 and dx2. dx1, dx2. Right. So this right here is the image of this dx under this linear transformation. 2x1, right? And actually, so let's evaluate it at this point 1, 1. So x1 is 1, right? So this just becomes a 2 at this point. So this is going to go to the vector, this dx is going to go to the vector, and the basis over here is going to be dy1 and dy2. But let's just go ahead and say, okay, this is going to be 2 dx1 plus 3 dx2. And where does this go? Well, this is going to go to 1 minus 2. So this is going to go to dx1 minus 2 dx2. And so what's the derivative? So the derivative is this linear transformation. It's exactly this linear transformation here. That's what the derivative is. So we can think of derivatives as essentially being equal to linear transformations. That's what a derivative is. It's essentially when we have a function, the derivative is the linear transformation that best approximates the function at that point. That's exactly what the derivative is. And that's why the derivative in higher dimensions is really a matrix. It's not a single number. And we have the determinant over here, and that is a single number, and that's essentially just the area over here. The area spanned by the image of these basis vectors. Right. So that's essentially what we're looking at. So finally, I want to conclude this video by looking at compositions of functions. So just abstractly, let's say we have this function f, and we have another function g, right? So this is going to map somewhere, and these basis vectors are going to map somewhere. And then again, we take the image of these basis vectors, and they map somewhere once again. And we can think about this composite. We can think about this composite transformation. We can think about, so we rewrite it is, so in this particular case, we do G composed with F, right? And I can think about, okay, what's, if these are functions, what's the derivative of this composition? at some point A here. Well, essentially what that's going to be is essentially that there's this linearity property, so that the derivative of the composition is a composition of derivatives. So there's essentially this linearity property of derivatives, and essentially what we get is that so actually in this example, so let's do G and then F, because that's essentially what we're doing here. This is going to be D, G of A, F, composed D, A, G. So essentially what this is saying is, okay, what's the derivative of a composition of two functions? Well, it's just the composition of the derivatives. It's the composition of these linear transformations here. Right? So this is essentially the chain rule, but it's the chain rule in higher dimensions. Chain rule in higher dimensions. So this is kind of the most general form of the chain rule. It's really what the chain rule says is the chain rule is essentially saying that derivatives are really compositions of linear transformations, and they follow this linearity property. That's essentially what the chain rule says in the most general case. So that's kind of the way to think about multivariable derivatives, is to think about these, say, basis vectors, take them, and look at the image under F. Think of F as an action. It's acting on the plane, or it's acting on three-dimensional space, and the derivative is the Jacobian, but that's just a fancy word for saying it's the linear transformation that best approximates the function at that point. And because we just look at where the basis vectors go, and that's essentially what we get.